You have to hit record like 3 times. All right. There we go. All right. So, again, if you forget everything I say today except this statement, you are doing okay. This is important too, though, and that's what the whole word quantize. In Regents Chem, it's not that big a deal, but AP Chem or College Chem, it's important to understand that concept of quantize. Those little boxes in lab, the orbitals that we're going to be drawing and putting arrows in, that has to do with this. Okay, so if you're in an orbital on the first level, you have a certain amount of energy, and that energy is very different than the orbitals on the second and on the third. So it's specifically quantized, specific amounts. That's what the word quantum means, a bundle of energy, and that's what this means. So it gains, whatever, 100 joules, then it loses 100 joules. It has to be the same, all right? And this is what creates light when it loses that energy, and depending on how much energy, changes the color of light we see. So if it's not a lot of energy, it's probably red. And that's a big, long wave. Kind of like that, big. And then if it's a lot of energy, it's probably violet. The wave kind of is squished together. So the red wavelengths are kind of big, long wavelengths from here to here. And this is what the video is. I'm going to show you a video again in a minute. And then the violet kind of looks like that. Now, that's really messy, but these typically will be the same height, just this is squished. So red usually has less energy, which means if an electron gains and falls and loses just a little bit, that kind of light's going to be given off. If it jumps up maybe higher, so you need more energy the higher you go, and it gives off more, that's maybe the blue or violet. So I'm trying to help you understand when you're looking at the sun, yeah, it just looks like white light, but really, there's a lot going on behind that light. Same thing here. All right. So let me show you the videos now about the waves and the spectrums, and then we'll learn about 2 other things today. A continuous spectrum, which is what you're going to see out the window. That's called a rainbow. Now, I want to be clear. When you look through those things behind Grant, it's called a spectroscope. Period 2 was totally confused. I don't know what they thought they were going to look through those, and everything was going to look like a rainbow. I don't know how I misled them, but I did. So they said, make sure you tell period 6. That's not what they see. You don't see. You have to look through it. You see rainbow color, but it's not like the building isn't rainbow. You'll see. And then the other word, so continuous spectrum, and then this other thing called a bright line spectrum. That's when you look at lights like this or in the gas tubes. You don't see a rainbow, you see these bright lines of colors. So it's called a line spectrum. So we're going to learn that today. We had to understand the basic first. The videos will help with that, and then we'll get those out. All right, so lights, please. Here we go.
Do we need our notes now?
Yeah, keep your notes out. We're not done with the notes yet.
Right.
So first thing here, let's get the first 2, please. What is light? Is this light? Here it is.
Homework?
Okay. Grant, time to shine. Oh, come on, Grant.
Yeah, what the heck?
No, Thursday. Sure. Okay. Yep. All right. Okay. Tristan, I just got called to cover a class next period, or 8th period. So we'll have to do it maybe tomorrow. Do you have the same period every day?
No, it's every other.
Thursday I'm leaving early. I don't know, we'll figure it out. I'll talk to you after class. All right, here we go. All right, so what is light? We saw the beginning of this yesterday. Here we go. Actually,
Light
yeah,
is
we
a
got
strange
some.
thing. It isn't just what we can see. Light can be broken up into different types, and we call the whole family the electromagnetic spectrum. So even when it's dark, light is still all around us.
Wait for her.
Light can be created by making an electron oscillate. This creates an oscillating magnetic field.
What's the deal here? What's going on? Gaining energy, losing energy. Gaining energy, losing energy. Right? That thing's an electron. Remember the whole wave thing.
And an oscillating electric field, which we call an electromagnetic wave or light. We often represent light as a wave. Just like water waves, light has a wavelength, a frequency, and a speed. The different colours of optical light have different wavelengths.
So again, red, really long wavelengths, violet, they're a lot closer together. Different energy. These are more energetic, these are less energetic. But the confusing part is all these are moving at the same speed. So like from here to here, it would take the same amount of time to go from here to here, but the number of peaks would change. That's the difference. The frequency changes. Frequency is how many of these peaks pass a certain point. If you take AP Chem or physics, you'll learn all about that.
And so does the rest of the electromagnetic spectrum. Gamma rays are the most...
So, those are all the main parts of the electromagnetic spectrum. These are really bad for us, radiation. Okay? Gamma rays, X-rays, ultraviolet, they can cause cancer. All right, these not so much because they're so big. Your skin can block them, and they don't harm your skin as much. So like ultraviolet, your skin can sort of protect you, and you get too much, and obviously you'll get a sunburn. But these aren't as bad for us because they're really big waves. This is the only part we can see, visible light. You can't see any of these. You can't see any of those, right? So that's the colors. That's where rainbows and the colors of things in this room. But yeah, these things are useful. X-rays to detect things. There's other types of radiation used to detect things like CAT scans and PET scans and all types of scans. Well, MRIs, right? It's a little different with MRI, but yeah. Anyways, we use radiation to detect like cancerous tumors or issues with your body, but at the same time it can cause cancer. So like, I don't know if you guys know this, you can't have just an unlimited number of X-rays in 1 year. There's like a certain time period. I don't know what it is. Let's say 1 X-ray a month or something like that. Like, you can't be exposed to that high level of radiation because then it really increases your chances of getting cancer from X-rays. That sounds crazy, but you really shouldn't need a whole lot of X-rays in 1 year. Like you're having a really bad year if that's the case. So anyways, I just wanted to kind of throw that in there that some of this is bad. Ultraviolet's bad for you. You're supposed to wear sunblock, right? Otherwise, it'll burn your skin. You can get skin cancer from that, and that's because it messes with the chemical makeup of your body, your skin. What's that? Okay.
Gamma rays are the most energetic, whereas radio waves have the least energy. Even so, light is the fastest thing in the universe. In a vacuum, all light waves, even radio waves, travel at an incredible speed of 300 million meters per second. The Royal Observatory is overrun with squirrels. They're hard to miss during the day because they reflect visible light from the sun, but at night it's more difficult. However, they do emit infrared light, and if our eyes could detect it, we would be able to see them in the dark. If we pass high-energy X-rays through them, the squirrels look very different. Humankind has invented lots of different instruments to show our atmosphere scatter blue wavelengths of sunlight, giving us blue skies during the day.
You found that fun.
I really like that. When the sunlight is more direct with the atmosphere, so the atmosphere is on a scale, some small scale, say it's this thick. The sunlight's going perpendicular to the atmosphere. It looks blue to us because the atmosphere scatters blue light. So remember, Roy G. Biv, all the colors of the rainbow coming at us right now from the sun. They're all mixed, so it looks white to us. But particles in the air can actually scatter that and absorb some of it, so the blue light is scattered. It's not really absorbed, it's scattered. All the other light is absorbed. There is red as well mixed in there, but you don't see that until the angle. So if here's your atmosphere and the sun starts to, obviously the sun isn't moving, we're moving, but the sun appears to be setting. So now the angle of the sunlight is going through the atmosphere at a different angle, all right? And more of the atmosphere is interacting with the sunlight, and that reflects red light a little bit better. So if I keep playing that there, they kind of show that.
And red skies at sunrise.
Right. So that's why the color changes, because the angle of the sunlight changes. I think that's really cool. Not a lot of people know that. I think it's good for you to know. The ocean is not turning the sky blue, and the sky isn't, well, is the sky turning the ocean blue? No. Is the ocean blue?
No.
If you had a cup of water from the ocean, would it be blue?
No.
Well, that's interesting, right? How we always It's just easier for maps and pictures and teaching kids and stuff like that. Water is blue, right? We always kind of, that's how we associate it. What's that? It does look blue.
You said it does look just the reflection.
But, yeah, I mean, it has to do with light, scattering. But anyways, let's not forget the ocean for a second. But the sunlight reflecting and scattering in the atmosphere, that's why it's blue versus different colors, pink, orange, red, yellows, whatever colors you see at sunset. I think that's cool, or sunrise. That's something we should know there. So what about planets that don't have an atmosphere? Mars doesn't have an atmosphere. Guess what color the sun looks like to that people that live on Mars
Red.
at all times?
Red. Black. Green.
Violet.
It's like white light. It's like white light. There's no color because there's nothing scattering the light.
Well, that's not cool. It's boring.
Well, don't go live on Mars then.
I'm not gonna work.
I'm talking about the atmosphere and the color of the
Yep.
sun.
But they don't have that.
Hi, I'm Rose Robinson. In this What Is video, we're going to take a closer look at the electromagnetic spectrum. What we see as light is only a small part of the electromagnetic spectrum. The electromagnetic spectrum refers to the many types of radiation released from stars, including our own sun. Electromagnetic radiation travels in waves. Frequency describes how many waves per second a wavelength produces. Wavelength measures the length of an individual wave in meters. Scientists describe the electromagnetic spectrum.
There it is. Cosmic rays are really, really skinny, really small wavelengths, up to radio and broadcast, which are humongous, over a football field long radio waves. They're really big. All right. Visible light is right in here. I think they put that in there. Here, I'm going to kind of speed through this a little bit. Well, here. I'll let you.
Spectrum is a long line. At one end lie radio waves, with the longest wavelengths and lowest frequencies in the spectrum. A single radio wave has the length of a football field. After radio waves come microwaves, which produce more energy due to shorter wavelengths and higher frequencies. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared light. The sun, fire, living creatures, and other heat sources all produce infrared light. While we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum, nestled between infrared and ultraviolet light. Red wavelengths have the lowest frequencies and longest wavelengths of visible light. As you move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase.
Okay. So these are nanometers. On your reference table on the front, it tells you there's 1 times 10 to the 9th nanometers in one of these. So a meter stick has 1 billion nanometers on here. So a nanometer is ridiculously small. So from this end to this end, you can fit 1 billion nanometers. So 400 nanometers, which is really, really small, that's purple light. So the waves traveling through the air, if it has that wavelength between these two crests, it's our eyes and our brain says, oh, that's purple. And if it's 700, then it's red. It's a little bit stretched out. Didn't I talk about slinkies yesterday?
Mm-hmm.
All right, you stretch the slinky out, you get more towards red, squish it together, more towards violet. D, you with me? Maybe just sit without leaning on your hand. I know, it's tough being a teenager. So blue, green, yellow, orange, there's somewhere in the middle. Okay, depending, again, the slinky analogy is pretty good. Depending on how much you stretch it out, that changes the color. I think that's really impressive and cool that our eyes and brain can figure that out instantly. Because just a subtle difference, this is a really small difference, it's a different color. Okay? So that's really what's in light. When the light we see, it's all these wavelengths just blended together. We can't separate them on our own. We need those things behind Grant we're going to get to in a minute. Here we go.
The frequencies increase. From visible violet light, we move into ultraviolet frequencies. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburns.
Who knew that? Not the sunburn, the vitamin D. Yeah, in fact, I think, I don't want to speak for doctors or people who know these things, but people throw the word they say go outside for a little bit before you put sunblock on so you get that vitamin D. It's good for you. Then you put sunblock on so you don't get this vitamin D anymore. It's just blocking the ultraviolet. So the UV rays, it's some of it like small amounts, like for me, you know, like 5 minutes, or else I'll start burning. So it's pretty fair. So that's another thing that's interesting, right? Depending on where you live, your ethnicity, race, your skin, your body can absorb and handle ultraviolet radiation better, right? So like me, I'm super white and fair, so I can't handle that, right? But other people, like my father-in-law is from Peru, he can sit out all day and he gets a little burn, but you know, I would be like in the hospital. He doesn't wear sunblock and he gets really dark, but he's okay. So it's just interesting. I wonder if he has more vitamin D than me in the summer. I wonder if that would work out. But it's just, think about that, how the skin, it can be different and how it reacts. But anyways, that's good for you in small amounts.
Next, X-rays, which pass through soft tissue but not denser materials such as bone, making them valuable for medical tests. X-rays also have security applications such as airport baggage checks.
All right, we're good with that. Now, before we get those things out with Grant, well, we can do that. Stand up, grab one of those things behind Grant. You're going to have to share. There's a lot of you. I want you to look out the window. You go in the back, you come up front, doesn't matter to me. I want you to look out the window. Look out the little end. The little end, yes. The little end is what you're looking through.
Alright, so are we looking at
Look through the small end.